And so let's take out this X part. With that being said, now that I have the correct shape of my table, I need to insert some good starting values, right? So what are the seed values here? Well, recall in our strategy, we said that basically the entire table could contain mostly zeros. So maybe I'll bake that right into this line. So after I make a new subarray, I'll be sure to fill it with some zeros. So if I run that now, I should have a nice table. Cool, so that's looking pretty good. At this point, I also need to seed another value, right? We talked about it in that we should seed table at position 1, 1 with exactly 1. Because it's sort of like our base case. When we have a 1 by 1 grid, there's definitely only one way to travel through it. So now we have the element of 1 in position 1, 1. Nice. So at this point, now I need to iterate through my table and fill in the position. So I'm going to use just nested loops for this. So I'll say let's I equal 0. And I want to make sure that I goes up to and including m, right? Basically the dimensions of the table. And I'll do I++. And very similar for my inner loop, being sure this time to reference j. And j is going to go up to n this time. Cool, so I just have classic nested loops, just iterating through this two-dimensional array, right? So as I'm iterating through the table, what was the logic we traced through in our drawing? Well, what I needed to do was take my current element that I'm at. So maybe I'll call it, let's say, my current. So my current element would be at table ij. So I need to take this current element and I need to add it into my right neighbor and my down neighbor, right? So if my row is I and my column's j, that just means I do some arithmetic on I and j, right? So if I want to increment my, let's say, right neighbor, what I can say is look at table at position I, j plus 1. That would be directly to my right. And I'm going to increase it by whatever this current is. If I want to look at my down neighbor, then that would be I plus 1, but I keep j the same. Cool. So this will add to my two neighbors that are to the right of me and below me. And at this point, what we have to be aware of is like what happens at our edges of this table. We know that if we're already at like the last position of a row, if I do j plus 1, then I'm going to go out of bounds. And so to make sure I don't step out of bounds on these increment expressions, I'll need some conditional logic. So I'll say if the right position is in bounds, so if j plus 1 is less than or equal to n, then I'll go ahead and increment it and it should be okay. And likewise, if I plus 1 is less than or equal to m, then I'll also increment, right? Notice that when I check my like j value, that should be using n, right? Because that's the number of columns, and then I is the number of rows, so it should use m. Cool. So what I have so far is, all right, I'm iterating through every position of my table. And I'm going to take the element at my current position, and I'm going to add it into my right neighbor, as well as my down neighbor, but only if they actually exist. Cool. So once I'm done filling up the table, then my final answer should just be at position mn, right? Just a very bottom right corner here. So let's give this code a run. So I should get 1336 and then this a very large number. We'll run grid traveler. Nice, and it looks like this solution is totally working. And we're already satisfying the last example here, right? If you tabulate off the bat, you will have a pretty quick solution. And we've already traced through the complexity for this. So take a moment to look at this code, let it sink in. I'll really try to understand how we took that whiteboard strategy and implemented it in some code, right? We do have to do some like kind of fine implementation details, especially with the bounds checking here. But I think the most important logic is about how our current position of the table contributes to our immediate neighbors to the right and downward. With that, I think let's head back into the drawing board. All right, now that we've seen tabulation in two different problems, hopefully you're noticing some patterns, right? Let's give ourselves some rules we can follow to tackle any dynamic programming problem using a general tabulation strategy. With this tabulation recipe, it's going to be pretty different compared to our memoization recipe in that there aren't like two main steps. When I talked about memoization, I said make sure you implement the brute force first and then add the memoization afterwards. Whereas if you just try to tabulate a problem, you're really going to have the most efficient version of your solution all in one swoop. And so what is our first step for tabulation? Well, of course, you have to visualize it as a table. And that really begins with a conversation of what should like the size or dimensions of the table be. That should definitely be correlated based on the size of the input. So in the case of Fibonacci of n, we made our table roughly, n elements long. Sometimes you definitely have to watch out for like an off by one scenario, which we've been seeing lately. In the case of our grid traveler problem, we saw that because our, problem represents a grid, we had to create a two-dimensional table at that. So figure out the size of your table based on the inputs to the problem. Cool. And once we do that, we need to initialize some values within the table. To me, this is always about choosing compatible types. In other words, if your problem asks you to return a number, then it'd be wise to initialize the values of your table with numbers, right? On the flip side of that, if I was asked to return a Boolean in a problem, then I'll consider initializing true or false within the table. Cool. And once I have all of the kind of generic values filled up in the table, then I choose my very important seed value, right? I know that this seed value should capture the scenario where I have a trivially small instance of the input where I automatically know the answer, right? So in the case of our classic Fibonacci, that means I just seed the n1 and the n2 values of my table with 1 and 1 respectively. And in the case of our grid traveler, we were sure to capture the scenario where we had a 1 by 1 grid. So you're going to need to seed those values because that's the basis upon which we fill the rest of the table. And then we have the hard part, which is really iterating through the table. And you have to come up with some logic, right? As you iterate through the table, you have to design some logic that fills further positions of the table based on the current position. And you really have to, look to the problem to figure out what the logic is. In the case of Fibonacci, it's as simple as if I'm at some position of the table, I look one space ahead and two spaces ahead, very reminiscent of the pattern Fibonacci. In the case of our grid traveler problem, it was about looking the unit to the right or the unit downward, effectively shrinking the size of our grid. So it's really, up to you to figure out the logic, look for language in the problem. What I always do is focus on what options I have at any point in the problem, right? My options are, do I go rightward or do I go downward in that grid traveler problem? So we'll stick to these rules as we tackle our tabulation problems, and we'll utilize them right now. Okay, so let's work on tabulating our CANSUM problem now. So recall that in this problem, what we want to do is take in a target sum as an argument, as well as an array of numbers. And we want to return a Boolean indicating whether or not we could generate the target sum by adding numbers in the array. And we can reuse an element of the array as many times as we want. We can also assume that all of the input numbers over here are non-negative. So we've solved this problem before, right? Recursively using memoization, but now we'll want to use a tabulation point of view. So let's come up with the strategy here. So let's say I gave you this input of 7 and an array of 5, 3, 4. In the long run, the answer is true because it is possible to generate 7, right? You can either do a 3 plus 4 or a 4 plus 3, and that would give you your original target. So you know that in the first step for tabulation, what we need to do is create a table. But I guess the question here is, what size table do I create? I have two inputs. I have the target as well as the array of numbers. Which of those actually contribute to my initial table? And so the key insight is to think about, what's going to change throughout the problem. In other words, if we can reuse the numbers of the array as many times as we need, then it's not like we're shrinking the size of that array. However, if we think about the target number or the target sum that we're given, we do have a goal of actually reaching that target sum, and we're going to increase to it over time. And so I'm going to use that as a basis for my table. That is, I want to create an array that is roughly the size of my target sum. So because the target sum is 7, I want to make sure that the indices line up perfectly, so I'll actually have to create an array with length 8. And in general, I just be creating an array of length target sum plus 1. Of course, we have that classic off by 1 error over here. All right, now that we have the correct size of table, what do I actually want to store inside? That is, what should the eventual elements of this array be? So a really nice rule of thumb you can use for that is to just recognize what type your answer should be in the long run, right? So here they're asking for a Boolean answer. So that really tells me that I should probably put some Boolean data as the elements of this array. So I'm going to start by initializing every element of this array with a false value. And the reasoning is, right now, we're kind of assuming before we check anything that none of these target sums are actually possible to be generated. Cool. But now I have to think about any particular seed values I need. Something inherent to this can sum problem is we treat the target sum of 0 very special, right? It's sort of the base that we use. In other words, if someone gave me a target of 0, I know that that is always possible, no matter what elements I have in the array. Because to generate 0, I can just take no elements of the array. So that's going to be a really important seed value here. So I'm going to populate index 0 with the element true. Cool. So now that we have some good seed value, now we want to think about how we can flesh out the other elements of this array, sort of in a linear fashion, right? So I know I'm going to have to iterate through this table. So let's just start at the very first index. So right now I'm looking at index 0. And if I'm situated in any position of this array, then the value I'm currently looking at should basically say, is it possible to generate that index amount? In other words, since I have a true at index 0, then I know that it is possible to generate 0 using the coins of the array. But now that I'm at this position, how can I actually transition into the further positions of this table? And so what I want to do now is consider the possible numbers that I can take into my sum. So I'm going to start by looking at this first element of 5. I know that if it's possible to generate 0, then if I also have a 5 in the array, then it's also possible to generate 5. In the context of my array, that means I should look about 5 spaces ahead from my current position. So I look at this spot, right? Exactly 5 indices ahead. And right now, I should actually replace this false value that's stored at index 5 with a true. And again, the reasoning is, if it's possible to generate my current amount, right? Right now I have a true in the 0. If it's possible to generate my current amount, and I could take a 5, then it means that the position 5 steps later should also be true, right? And I want to actually continue this process for the other values in my numbers array. So I'm just going to look at the next element of 3. And that's basically telling me that, hey, the next spot 3 places away should also become a true. So I'll just go ahead and make that a true. And finally, likewise for the last element of 4, right? The element 4 spaces ahead should also be turned to true. Cool. And at this point, I think I finished like my very, very first iteration. That is when my current is at index 0. And at this point, I just want to keep iterating through the array. So I'm just going to shift my point of view 1 space to the right. So now I'm looking at my current as index 1. Notice that over here, my current element is actually false. So what that means is it is not possible to generate 1 using the numbers of the array, which logically makes sense, right? I only have 5, 3, and 4, so there's no way you can ever give me back a 1, right? So if I have a false value at my current position, then I should not modify like my further values by looking ahead. So notice that if I look at my edge for 5, if I look 5 spaces ahead, I am not going to make that a true because my current position is not true, right? So I'm going to keep iterating. Same thing happens when I'm at index 2 because the current value is false. There's nothing to be done here. Things get really more interesting on this iteration, right? If I'm at index 3 as my current, then I see a true at this position. So that means I need to look ahead to my future positions and actually assign them to be true. Obviously, you'll notice over here, if I look 5 positions ahead when I'm currently at index 3, then that would actually be out of bounds. So I don't need to look that far ahead. So we'll kind of drop that connection. But at this point, I should make the space 3 positions ahead true, as well as the space 4 positions ahead. So that means that indices 6 and 7 are set to true, right? And I keep doing this process all the way through the entire table. Notice that as I keep iterating toward the right, these forward-looking references kind of stop being useful because it goes out of bounds. But the point is, by the end of all of these iterations, I do have a true stored at index 7, which means that it is possible to generate a quantity of 7. And if I do a quick spot check and I look at just my entire table right now, it has very consistent data. In other words, if I notice where all of the true values are, right, they're at 0, 3, 4, 5, 6, and 7, that means that all of those quantities for target are actually possible. Right? On the flip side, if I look at the only elements and indices that are false, like 1 and 2, that makes sense because those are the only quantities that are not possible, right? You can't possibly generate a 1 and 2 using a 5, 3, and 4 as your options for adding up, right? So we know by the end of this algorithm, the element that is stored at the last position of our table would be the final answer, right? So if it's true, then it's possible. If it's false, it is definitely not possible. All right, so let's wrap up this sketch by actually talking about the complexity of this. As always, we'll define our terms. So we'll say that m is going to be the target sum, which is just a number. And on the flip side of that, we'll say that n is going to be the length of the numbers array. And we already have the vibe that, hey, both of these terms definitely affect our complexity, right? If you give me a larger target sum, then it's probably a harder thing to calculate. In the same way, if you give me more numbers to choose from, it's even harder to calculate, right? And we can recognize that the algorithm just has us flesh out this table. And I know that the table is of size m, so we're going to have at least m. However, as I iterate through every position of the table, what I had to do was actually look ahead in the table for every single element of the numbers array. So I know that that's going to be accomplished basically using some nested loops, where I'm going to have a loop to iterate through just the table, and then a nested loop to iterate through every number of the numbers array. So overall, I'm looking at an m times n time complexity. And along with that, what is the space here? Well, the space is really just the exact size of this table, which is based solely on m. So I have just m space overall. Nice. So this is already looking like an efficient implementation, especially because we're not dabbling with any exponential complexity over here. I think let's work on the code now. So here we are, back in the code editor. Let's start like we usually do by creating our table. So I'll store this table, and like we discussed in our drawing, we need to make it roughly the size of our target sum. So I'll create an array, and I need to make sure that the indices line up directly, right? I want an index that is exactly the target sum, so I'm going to initialize it to target sum plus 1, right? So that means if I pass in target sum as 7, I'm going to create an array of length 8, which means that its very last index is 7, though, which is perfect. Cool. And while we're here, we'll go ahead and actually initialize this array with all false values. So I'll do that. And I need to make sure that I seed index 0 with a true, symbolizing that the target sum of 0, it's always possible to be made even before I look at what's in the numbers array. So I'll just go ahead and say table at index 0 is equal to true. So let's just console.log what this table looks like so far, and I'll just run, let's say, the second example here. So I should see my array of length 8. Nope, I need to go into this tabulation folder. Now I'm going to run this guy. Cool, so that looks like a good table, right? 8 elements, and I do have a true at index 0. Nice. So at this point, now I want to actually lay out the core algorithm by iterating through the table. So I'm going to use a regular for loop here. I'm going to say let I equal 0, go up to, I can even include if I wanted to, up to and including the table.length. I guess you could also say a target sum here, some thing based on target sum. I'll do I++. And here I'm going to choose to iterate using the manual index, because I know I have to do some arithmetic to look ahead in the array. But as I iterate through every element of the array, I want to actually check if this position is true. So I'll check if table at index I is true. Cool. Because I know inside of this if statement, I need to basically jump ahead or look ahead based on what's in my numbers array, but I only need to do that if my current position is true, right? I only get to look ahead if it's even possible to get to this current amount, right? The current amount I'm sort of tracing through, it would be at index I. So at this point inside of my if statement, what I want to do is now look ahead for each number of this array. So I'll nest a loop here, and I just want to look at the elements of this array. So I'll say for, let's say let num of numbers. So I'm grabbing each element this time. And now for this number element, I want to look that many spaces ahead. So I want to look at basically table at index I plus the number. Cool. So imagine that I'm on like the first iteration of this. I know I is going to be 0, so that's the very, very first index of my table. And if my num is 5, then I'm going to do 0 plus 5, looking 5 spaces ahead, right? Just like we did in our trace. And for this position, that is like 5 spaces ahead, I want to assign it to be true. Basically saying that, hey, if my current position is reachable, and I can take a step of exactly num, then that must mean position I plus num is also reachable, right? And that entire for loop goes inside of this if statement, right? So this code is looking pretty good so far. I think the last thing we need is just to return our final answer after we're done iterating through the table. So here I'll just return table at index target sum. Cool. So let's go ahead and run these examples. Maybe we'll have to debug some stuff. Looks like I have probably an infinite loop. Yeah, my program crashed with some massive error. So let's debug this one together. There's something that I'm not considering in my code, but we did consider when we drew it out. So something that is probably breaking right now is having to do with like the bounds checking. Something that's kind of unfortunate in JavaScript is this characteristic. This may have different behavior depending on the programming language that you're following along in. But I know in JavaScript, if I had some array, let's say array, and I set it equal to just a handful of elements, let's say A, B, and C. If you actually do like array at some out of bounds index, like index, I don't know, 10, and I assign it like X, that will actually change like the effective length of this array. So if I take a look at what happens here, so I'm just running this kind of offhand example. When we run this, notice that we have about 7 empty items before we have the X. Basically, when you do this type of weird assignment in JavaScript, it's going to like lengthen your array. That way it makes sure that this, hey, new element of X is placed at exactly index 10. And so why is that relevant? Well, in my code here, I don't really check if I'm out of bounds, right? And I just assign to something that's potentially outside of the current length of my array, of my table rather. And if I do that, then this condition is a little suspicious, right? Because if I do this assignment on line 9 to an out of bounds position, then the length will get longer. And that's sort of like a circular argument, right? I keep iterating only to make more stuff out of bounds, only to lengthen the table even more. So that's why I ended up with like an infinite loop over here. One way I can fix that is to just maybe limit this. So I won't make a table.length. That's a little too dynamic. I know I can basically stop once I reach the target sum. So that might actually be the better move over here. Pretty fair bug though. With that, let's go ahead and run this code again. Give that a shot. And here we see true, true, false, true, and false, and that is the correct answer over here. Nice. So here's a nice tabulated solution for our CANSUM problem, and we already spoke about this code having an m times n time complexity. Now it's really obvious, right? Because I can see these exact loops, and our space complexity is simply based off of m, right? Cool. With that, let's head back into the drawing board for another problem. All right, now let's work on the HowSum variation of this problem. So like before, I'm going to take in the target sum as well as an array of numbers, but this time around what I want to do is return an array containing a combination of elements that actually adds up to the target sum, right? So here I want to return exactly one way if it's possible. And along with that, let's say that it's actually not possible to return the target sum, then I should just return the null value. And if it's the case that there are actual multiple combinations that can generate the target sum, I can return any one of those. So we expect the strategy for this one to be very similar to our last problem. However, we will need some nuanced logic to return the array now, right? Because I don't want just Boolean data, I want to return an array. So let's sketch this one out. Let's say I'm stepping through this example where my target is 7 and my array is 534. For this input, a reasonable answer to return would be an array of 3, 4, right? Because I can add 3 plus 4 to get 7. You can also, I guess, switch around the order of these elements. So if you also returned 4, 3, I think that would also be a valid answer. Point being, I just want to return at least one way that I can generate the target. So we know we want to solve this one with tabulation, and so we'll just follow our recipe, right? I need to construct and initialize some table. And we already know that the size of this table is going to be based on the target sum. So roughly 7 elements, but we of course have that classic off by 1 nature, right? Because I want the last index of this table to align with the actual number argument. And in general, I'm going to initialize this array with a length that is target sum plus 1. Cool. So now that I have the correct shape of table, what do I actually have to initialize as elements inside of this table? Previously, in like the Boolean version of this problem, we initialized everything as false, right? And the reasoning there was before we actually try all the possibilities, we're going to just assume that it's not possible to generate every quantity. We just want to adapt that for this new type of problem. They tell us that if it's not possible to generate an amount, then we should just return null. So I think null is actually a great initial value to just put everywhere in your table. So at the start, we're going to assume that none of the values or none of the amounts are actually possible to be generated. Null is sort of the analog for false in this rendition. Cool. So now that I have most of the values added to the table, now I need to figure out what's an appropriate seed value. That is, I need some actual data to begin and get the ball rolling on this one. So like we expect, it's about having an amount of 0, right? No matter what, if you're given an amount or a target sum of 0, and no matter what array of numbers you're given, you can always actually generate that quantity of 0 by just returning the empty array, right? You can take 0 elements from the numbers array, and there you have an array whose sum is 0. So of course that means at index 0 of our array, we're going to initialize it with just an empty array. And at this point, what we want to do is, of course, iterate through our table and come up with some logic we can use to fill out further positions of the table based on our current position. So let's say we begin at index 0. So here I am, and I have to figure out which further positions of the table should I be looking at. We've seen this pattern before. I should just base that off of what I have as options in my numbers array. So look at my first number of 5. That means I could look exactly 5 spaces ahead in the table at this position. And so if I know that my current position is possible, right? I see that I have an array in my current position, that I know it's possible. If this current position is possible, then a position exactly 5 steps later would also be possible, right? And so what I'll do is I'm just going to copy my current value into my further value. In other words, I'm going to put an empty array at position 5, right? However, I also have to include the number that I'm using right now, right? I took a 5 to actually get to this position in the first place, so I'm also going to add a 5 into that array. Cool. If I do a quick spot check, this is a reasonable thing to do because if I look at the state of that index 5, it contains an array of 5, meaning that, hey, you can return a sum of 5 by just taking a single 5. And with this, I want to do the same logic for the other numbers of the numbers array, right? So if I have the 3, I'll look 3 positions ahead of my current place. And I'll also start by copying over the array at my current position. So I copy over the empty array, and after I copy that array, I actually want to populate it with the number that I took to get to the spot in the first place. So I just go ahead and put a 3 in that array. And the same thing happens for the 4. So if we go to the next iteration, we see that our current element is null. That means that the amount, right, in other words, our index amount, is actually not possible. It's not reachable, meaning we can't get an amount of 1 by adding up any numbers of the given array. So what I should not do is actually manipulate any further values from this position. So I just continue these base iterations. Same thing happens when I'm at index 2. But things get more interesting when I'm at index 3, right? I see that the element here is not null, so it is possible to generate 3. And so what I want to do is go ahead and look at my forward values and sort of copy my current array over. So I know I don't need to look 5 spaces ahead because that would be out of bounds. So I'm going to look at the position exactly 3 spaces ahead in the table and copy over my current array like this. What I also need to do is make sure that I include the number that I'm using right now, which is 3, right? Because I'm looking 3 spaces ahead. So I end up with 3, 3 at index 6 of my table, which is reasonable, right? I also want to do something very similar for the position 4 spaces ahead. So I'm going to copy over my current array, but then also include the 4 that I'm using up right now. So now I have 3, 4 over here. Cool. At this point, you can kind of see where this is heading, right? I've actually already populated index 7 of my table, and 3, 4 is exactly one way we could create the 7. So we could stop here. However, let's say that you continued the algorithm. So in the next iteration, I know that this space 4 indices ahead would be out of bounds, so I don't need to look there. But according to our general logic, I would actually manipulate the spot of the table 3 moves ahead, right? And so what I'll do is if I follow the same exact logic, or I'm being consistent, I'm not really changing any of the rules here, I would copy over my current array into that position. So I'd basically overwrite index 7 with just an array of 4. But then at this point, I would also be sure to include the number that I'm using right now, which is 3, right? Because I'm looking 3 spaces ahead. So I end up with 4 comma 3, which happens to be like another way I can generate these 7. So it doesn't matter if you actually continued this algorithm. All right, so if I continued, I would basically just keep iterating until I hit the very end. And what do I know? The element at index 7 is exactly an array of 4, 3. Cool. So the point is, you actually don't have to like exit early. As you iterate through the table, you'll be okay to just finish all of your iterations and you'd still have a valid answer, right? Because in this problem, they just want any way to actually make the target. And if I take a quick look at my table, I think all of the stored values here make some logical sense. For example, if I look at index 2, there's a null, meaning that it's not possible to make a 2 using elements of the array. In a similar way, if I look at index 4, there's a subarray of 4, meaning you can just take 1 4 to make a sum of 4. Similarly, you can take 2 3s to make a sum of 6, and of course you can make a 7 by doing 4 and 3. So now that we have a plan of attack, let's look at the complexity for this. So of course the m will represent the target sum, and our n will represent the length of the numbers array. So if we begin with just the time complexity, we know that we're going to at least iterate through the table. And the table's of size m, right? So I have at least an m in my time complexity. But for every space in the table, or in every iteration of that loop, I need to also iterate through all of the numbers in my number input array. And so I could multiply by n over here. Nice. But at this point, now let's say that I actually need to take a valid step here. Then what I also did was copy over the array at my current position into that forward-looking position. And I know that a subarray will be at most of length m, right? Remember that m is our target amount? The worst possible or largest way we can generate the target sum would be to have an array of exactly m ones, right? And so we'll say that in the worst case, we have to copy over an array of an additional length m. So that means our time is really m squared times n. Now let's come up with the space complexity for this. We know that the initial size of the table is definitely based on m. However, in the long run, we could be storing a subarrays as elements. So this is going to actually be a 2D table in a sense. I know that the size of any particular subarray here is also going to be m for the same reason we just said. And so we have a m squared space complexity. So overall, we're pretty satisfied with the complexity of this because it's polynomial, right? It's not an exponential quantity, so it should run in a reasonable amount of time. All right, I think we're ready to hop into the code for this one. All right, programmers, back in my trusty editor, let's go ahead and tabulate this one out. So we'll need to create the table to begin, right? So I'll create my table, and it should have roughly target sum positions in it. Really, I need to increase it by 1, so I'll say array, and I'll pass in target sum plus 1. That way the final index aligns. I'm going to go ahead and fill this table up with all of those nulls, right? Exactly what we did in our drawing. What I also need to be sure to do is make sure we populate index 0 of our table with an empty array. Serves as sort of like a base case, in that we know that the target sum of 0 can always be generated, right? You can generate the target sum of 0 by taking no elements from the numbers array, right? If you took the sum of this array, it would be 0. Nice. At this point, we need to iterate through our table. So we've seen this code before. I equals 0. Go up to, and I won't mess this up this time, I'll go up to and including target sum, and I'll do I++. So far, very similar in shape to our last problem. Now that I'm iterating through every element of the table, I need to add some conditional logic. If you remember from our drawing, we only did like the heavy logic when our current position was not null, right? Because if it is null, then you can't even reach this current position in the first place. So I'm going to check, hey, if my current amount is attainable, in other words, if table at index I, which is my current amount, if that is not null, right? If it's not null, then I can generate amount I. Cool. So if I can generate amount I, then I know some other things could also be generated. That is, I want to look forward in my table for every number in the numbers array. So I'll say let num of numbers. So I'm getting the elements of the numbers array, and I need to look that number of positions ahead, right? So if I'm at I right now, that means that a forward-looking position would be at table I plus num. Cool. And I need to assign something over here. So what I'm going to do is start by copying over the subarray at position I, at my current position, right? I know that if table I is not null, then the only possibility that it could be is an array, right? It could be an array of 0 elements, or it can be an array of many elements. So no matter what that array looks like, I'm just going to copy over that array. So I'm going to spread out all of the elements of table I. And so far,